I'm going to teach you a new way of looking at quantum numbers as quantized hemispherical coordinates. That is, instead of it being an N, L, M, and S, I want you to think of this as your radial number, your inclination or latitude number, and then your phi, followed by which hemisphere in. That would be an N. Now, this all starts as the most basic challenge in physics. And that is, we have equations in a whole bunch of different frames of reference. You see, when you're talking about the normal space, is x, y, and z, and you can do x squared plus y squared equals 0, c squared. That's the Pythagorean theorem, which is very nice because each of those is independent, 1, 2, 3. And if one term changes, the other one doesn't. They are all isolated. They're all independent. And in a language that we're going to learn, they are all invariant. That means if you change one, the other doesn't change. Okay, that works very good. But of course, that's not what happens at the subatomic level. In the subatomic level, you have basically, here, let me get you an example. I'm going to make this a little bigger. You basically have a ball, which is a whole bunch of electrons, and they're sticking out in different directions, evenly spread, with some rules I'm going to show you, around a sphere. Okay? And so there's two things to learn. First is that electrons are in big shells that are generally round, a little bit prolate, oblong along an axis, but spherical. So Einstein came up with a whole bunch of adjustments to make sure and convert from x, y, and z into spherical coordinates, which is r, the longitude, and the latitude. Of course, that's all good, except there's another thing. They come in rings. So there's a big long axis, okay? And then in this end, if I'm looking at it from the pole, you have 1, 2, 3 around the edges, okay? They're at the same, let me put this way, with that axis, let's see, okay, sticking out this way. So no matter where you look, these, you see if I spin them around, they're at the same angle, this angle to that angle, okay? And we do this with the tetrahedron in carbon and in many other places. So all 3 electrons are at the same angle and ultimately at the same distance from the nucleus. That makes them the same energy, and they like to find these balanced places. Now, the other thing is that they want to be repelling each other. They want to be as far away as each other. And that gets the second rule. And that is there are hemispheres. So if you take this electron, all right, let's take, where's the axis? This electron, over here at 120 degrees, you have the Pauli pair. You see, the math is that everybody wants to be as far away as possible. So this explains the hemispheres. Nucleus and electrons and all subatomic particles have an axis. They have this from 3 different forces. Now, that means that you get this interesting logic. The shells are 2 hemispheres in 1 dimension, but then the tightest fist has to be in that other dimension. Okay, so this dimension is 2 Pauli pairs, and this dimension is a circle. If I go around that, that's a nice circle. And that's because the most balanced, the tightest fit of 3 atoms, or 5, or 7, or 9, is a circle. And here's some of the amazing math that does that. So if you have a shell, the first one has 2 hemispheres times 1 squared. So that's 2 electrons in it, subshell S. But for the second one, the shell 2 can have 4, that's the 2 squared, times 2 hemispheres equals 8. 2 times 3 squared equals 2 times 9 equals 18. And 2 times 2 squared is 16 equals 32. So that's actually not that difficult a math. We're not, rocket science here. It's basically squares, okay? Now, why is there 2? Well, I again told you a little secret. These are at 180-degree positions. So if this one over here is going down or up here, this one starts up here and then down. You can't see the other ones on the other side. That means that if you take another level and you rotate it half a phase so that the north does the south and the south does the north, then you can fit another layer in at the same count. That's why there's 2 and then 3, both at the same count, because this one, but this one's top, and say this one is bottom, then the next layer will reverse, and it can fit in there before you go to a bigger count. So that's why you get these strategies, okay? But there's even one more amazing things. Adding the odd counts gets the squares. What do I mean? Well, look, if you take 2 times 1, that equals 2. But now take 1 plus 3, the odds, and you get 4. Well, that's the same 4 we had up here. So that means as you add these things, as you look at this from the polar view, you get 1, 3, 5, 7, or 1, 3, 5, 7, 9, and so on. 1, then 1, 3, then 1, 3, 5. This is how the subshells orient. And remember that the opposite ones are from this 3 has the 3 over here, this 1 has the 1 over here, the 7 has the 7 over here in the other hemisphere as the Pauli pair. This is, again, very, very simple math, okay? You don't have to be an expert. But 1 plus 3 plus 5 plus 7 equals 16, which is 2 squared. Or sorry, 4 squared. What did I do on that schedule? All right, so why does that work? Well, if you take x plus 1 squared, you get 2x plus 1. So what happens with this? See, when you have, why does that work? And why does that create both quantum mechanics and also everything in chemistry? Okay? If you look at that axial plane, okay, I'm going to look at it. This is the pole, and this is, say, 3. So this is the subshell P in one hemisphere. Okay? And this one down here has one way up here at 180 degrees going the exact opposite way with a ring of that size. Now, look, these are pretty much evenly spaced around. Now, look here. We can have them evenly spaced, and the red is the electrostatic. Like kind repel. Opposites attract. Those electrons are attracted into the nucleus, but they are repelled from each other. In fact, my proposal is that they're attracted not just to the nucleus, they're also attracted to the nucleus axis, the nucleostatic axis. As a result, you get 2 equilibriums. One is the radial electrostatic, that's what we all know, like kind opposite, and then you have the opposite, this extra 1 over r, and that becomes eventually proton, neutron, proton in the nucleus, it's strong force, but here it's called angular momentum. Now that's not the right logic. Basically it's just an extra 1 over 2, 1 over r squared, which is the strength going down based upon this nucleus axis. So instead of having x, y, and z, you have x, y, z, and this axis. So instead of being a field of 1 over distance cubed, it's a field of 1 over distance to the 4th. That's fields. In accelerations, or forces, that would be 1 over distance squared versus 1 over distance cubed. Now you can see this all the time. So as a result, we get two basic things. You have the electrostatic proton-electron, attractive in red. You have the strong extra 1 over r, repulsing it, so that keeps it in balance, dynamic balance between the two. And in this direction, you get a very dynamic. You get pulled to the nucleostatic axis, that's the weak force. And those electrons, though, are repelling each other. Now, this is not a one-to-one result. You see, you have to add up all those red repulsions, and you get, because they're on different sides, the sideways don't happen. It becomes directly out to offset that directly inward to the axis. This is a polar view, so you're looking at the axial plane, and you see that the math works so that you can have radial, electrostatic inward, versus extra 1 over r, outward. Axial, the weak force inward, and the electron to electron repulsions. Now, the other interesting thing is this outward is multiple electrons repelling it, so there are collisions. They're all trying to fight to get to this pole, which means that you don't get a nice stable one-to-one relationship as in classical mechanics. It's at this level that you get the harmonics of quantized statistical, that's usually called the word quantum, mechanics. And that is the work to predict these, even if they're not locked in space, but they have these two dynamic forces that are generally equal if they were ever at Kelvin 0 and not moving at all. Okay? Now, so let's go up here and look at this. So how do we know this? Well, your textbook actually already says it. Your textbook has this underlying graph. I've put the names up on the top. So if you look, you can see that, for example, the S, subshell S, likes to have a polar bond. Well, that's the two at the poles, okay? So that one particle, that proton, say for a hydrogen, really has two sides for a hydrogen bond, inward and outward at 180 degrees. In other shells, you get down at these different angles, like I showed up above here. And so you can see rings in two hemispheres. One, those two cylinder, and there's the opposite one. There's one, and there's one. There's one, and there's one. These are fun. And the basic proof of statistical mechanics, this process over here, is done by Bose. He sent the paper blind to this guy called Einstein. Einstein was so impressed, he himself translated to German and sent it off and demanded that it get published as a new approach. And then he used it himself, that Bose technique of multiple collisions, to determine as a cylinder surface, he called it, with 2x for polarity. A cylinder surface with 2x. For me, that's hemispheres, and that's the cylinder, the Bose 2 cylinder. Now, obviously, if you're at the poles, there's no sort of cylinder, and so that's something called Gaussian, and this is called Slater type, and you'll find these in your advanced classes to understand exactly what is the difference and how do you solve the math equations that underlie these things. So now, what does that do for the electron shell system? So instead, we get two different things that happen. They go from pole to equator, obviously trying to fill subshell S first. We all seen that. But then they try and count these and build them up. Okay? Now, the interesting thing is that you'll see 1, 3, 5, 7, again, the squares. But what happens to those odd counts? Well, again, if you do the fancy math, you'll find that you can sort of slip a 3 in here in the middle, okay, at the equator for the electron configuration exceptions. And because of the combination of the Bose cylinders and this equatorial from my work, you now have a model where you don't have partial subshells. In my evaluations and work, you only have full subshells. So you can have, except obviously the first column and the last column, which become ionic. And so let me clarify that that is for covalent bonding. You must have full subshells, covalent. So if you have column 1, that's just 1, and it likes to release that electron and become an ionic bond. If you have 2, you get a polar bond. If you have 3, you might get a triplanar because you have 1, 2, 3, and they're right all around this equator. This happens in boron fluoride. Okay? If you have 4, you sort of get this odd 1 in this end and the full 1, 2, 3 on this end, and that becomes the half cube of a tetrahedron, which is the carbon, which is probably the most important molecule in our universe. It's the one that's the basis of amino acids, of proteins, of everything. And we'll show that in later courses. So now you have basically a model, say, for column 11. Let's go to over here to the most amazing one. In column 11, you would have 1, 2, plus the 3, so you'd have 8, 4 in each hemisphere. But you want to get to column 11, so you have 3 left over. Oh, well, I can make an odd count 11 because I can add 3 here. And as a result, I have full, 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 and full. But guess what? With those 3 at the 11 at the equator, they're sticking out. They are in the band gap distance, and they become electricity. So using this longitudinal model, you can find and understand electricity. Okay? You can also understand magnetism. Okay? If I take, say, the column 8 of, say, iron, now let's look at this nucleus to each of those electrons. You can see that, guess what? They're pretty much already aligned. So as a matter of fact, that outer shell tends to aggregate and depends on what happens to it, whether it's going this way or whether it's going this way. I'm doing the right-hand rule, which is something you'll learn in advanced engineering, okay? But as you do that, these are pretty much aligned, and so an iron atom would work that way. Now, if you thought about those extra 3, a column 11, so a copper, which is very electrically conductive, as I showed you right above, instead, those would be interfering. So you'd have a whole 3 going this way, 4 going that way, 4 going that way. It is almost impossible to get a copper atom in column 11 to be magnetic. It can be electrically conductive when these is just these 3 and there's no other one, so it's easy for them to move out and out, but it's not electrically conductive. So using my model of full subshells and the hemispherical quantum numbers, I can describe actually the chemical properties in the periodic table. So let's go to the final step, okay? As I said before, as you build these, if I look at them from the pole, those interlacings mean that this one is up, this one is down, and that one is up. So that actually the energy, the distance to say layer 4 or 5 is not straight, okay? But for the subshell S's, they're all lined up. That means you get what is officially called prolate, okay? And if you understand prolate, the Nobel Prize of Ange-Bohr and Koppelman basically proved by experiment that the nucleus is prolate. Prolate's a fancy word for oblong. Along one axis, it's a little longer than it is here. Now, you say, well, how do you know that? Well, we actually know that, again, going back to chemistry. When you get to chemistry, we talk about when you have subshell S and subshell D, those are the 5 times 2 hemispheres and 7. They have lower energy cells. So remember, this is one hemisphere, and these things all flip from this side and they go around to the other side. So I'm just showing one slice of one quadrant of a hemisphere, okay? So the subshell S's all line up in a straight line. But the off-axis ones, as I showed up here, are diagonal. So they get a little closer, 3, 3, 5, 5, 7, 7, and so on. That means that if you're measuring this distance here to 7, that's about the same distance as, oh, only this shell. This circular shell will get you there. So that for subshell D or subshell F, you get it filling in the order of n, but with the energy of n minus 1 or n minus 2, respectively. And that's based upon this simple 3D geometry. It is not strict off-ball, which I've shown over here, where you were told these go in this strict order. They do not, for 2 reasons. One is because it's really about the more complicated prolate hemispherical structure of atomic shells. And 2, it's not strict. You can have items that don't go in the orders. For example, the odd count exceptions, which I described up here at the top. So now, finally, with all that background, I can explain to you what is a quantum number. Well, a quantum number is first, how many layers do you have? Okay, are you in the first layer, in which case you would only have 1 at each of the poles. That's a helium atom, okay? Or as you build up, you can fit more in these structures. Probably easier to see it over here, okay? So as you fill up, this first one has 1, that one has 1 and 3, and then of course there's the ones in the offset by a half phase down here. Then you have 1, 3, 5, then you have 1, 3, 5, 7. Now notice that in this configuration, I left out the 3. This would be 1, 3, and 7. This would be times the other hemisphere, so that's 20. So when you go out to the 20th one, this is only in shell 6 or 7, it can have, and it will go fill subshell D if the count is right to keep them full before it fills subshell S. That's actually rules that we somewhat know. But mine solve all electron exceptions, including the odd counts, okay? There are no partials. So now let's look again. As you were taught, okay, there was an abstract numbers, and they solve a lot of things. The abstract numbers of quantum numbers give you this angular momentum one, this magnetic one, and this spin one, okay? And those were good names 100 years ago when they understood it. But I can tell you that the same thing is better understood using quantized hemispherical coordinates, the same numbers exactly, but they are the radius number, the longitude or inclinations. I use inclination because if you count from the equator, it's a longitude. If you count from the poles, it's a inclination. They're the same thing, it just depends on which direction you're counting. And since I count from 0, because the 0 count, subshell S, is 0, and that has meaning. That converts you from the Gaussian to the Slater and all the other calculations that you get if you get into advanced chemistry and physics. The phi is the latitude, and the z is plus or minus for half for which hemisphere you're in, with the Pauli pairs locked at 180 degrees. So now I have a new way of looking at things that I think anybody at any level from 5th grade up can understand not just chemistry, but also the advanced concepts of quantum numbers.